All right, we are recording. Let me get the set up from current slide. Okay. This will be the last time I announce it. Sorry, Ian and Amanda, if you were in here. But the College Scholars Bowl, y'all heard it enough. You know about it, so I probably won't announce it from now on. Okay? See Mr. West or one of these two fine people here. Now, two things. If any of you tried to get on Blackboard this morning and couldn't, there was some sort of emergency failure of Blackboard. They've gotten it fixed, so it should be back to its normal lousy self. So anyway, that was one. There's also, for the last month, we haven't been able to order anything because we've been trying to close out the business office for the year. And then this is a reminder, the business office is in the process of closing out data for financial reporting, and they're telling all of us, full-time employees, do not add, drop courses for students, award or process any grant aid, or complete registration until further notice. So if you were trying to register for something second mini-term or that type of thing, you can't do it now. Hopefully within a day or two you will be able to, okay? I can't say when. They didn't say when they would, but that's what that announcement. And what this is the administrative calendar, and they said here business and cashier's offices are closed. I've been trying to get in touch with the accounting, the personnel accounting, because we had two issues with payroll for adjunct instructors. I couldn't get anyone to answer a phone. Now, I guess it's because the offices were closed. Figured they'd still be in the office. I thought they just were closing it up outside, but they weren't even answering phones. But one of them did return an email, so at least that's happened. This one's important, not for you folks. You folks are here, okay? It's more important for the folks who are not here, okay? This Friday, the 4th, and Amanda is here. Okay. All right. This Friday, October 4th, is the last day to withdraw from a mini-term 1 course. That would be this one. I'm not suggesting that anyone withdraw, certainly not the people here. Y'all are doing quite well. It's some of the people who are not here, who have not turned in a bunch of stuff. They need to know Friday's the last day to withdraw. Otherwise, it could be pretty tedious. Okay. And I'll get back to something there later. They have some things about the final exams for mini-term 1. They say those are supposed to be Friday. That's kind of ridiculous, because what if someone's taking 2 or 3 courses on first mini-term? It would be really hard for them to take all the finals in the same day. So we will have our finals on Thursday. Okay, and here we get some more folks coming in. Here's Latricia and Edward. All right. Anyone else come in while I wasn't paying attention? Okay. And second mini-term, if any of you are going to be coming to second mini-term classes, they start on Monday the 14th. Okay. Our volleyball team, by the way, I had the student in class this morning, one of my students this morning was on the volleyball team. I asked her how the doubleheader went. She said they won them both, so that was good. Tomorrow they'll be playing Wallace State Huntsville. Unfortunately, they'll be playing in Huntsville. So it's not that far away. So if you happen to be anywhere close to Huntsville around 6 o'clock in the evening, stop by and cheer the team on for victory. Okay? And I'll announce the rest of those later. All right. Are any of you planning to graduate this December? Any of you? One. Okay. Is that all? Okay. Do you know about the upcoming mandatory graduation meetings. Have you heard about it? You have? Okay. That's Thursday the 3rd on this campus at 1 o'clock, on the Birmingham campus at 5:30. Okay? And the graduation application deadline for fall term is September 30th. They sent the email on October 1st. So that's really good to let us know in plenty of time. Okay. So please, if you haven't gotten your application in, please get it in immediately, if not sooner. Okay. Now, another, and this one has financial implications. Scholarship Summit for fall 2019. Are you an upcoming graduate? Now, that doesn't mean just for this term. That could be in the spring or even summer. Do you plan to transfer to a university? Or are you unsure of how to pay for the remainder of your education? Come educate yourself on the college transfer process and transfer scholarships opportunities available from some of the leading colleges in the state. This will be 2 days next week. October 9th, that's 1 week from tomorrow, will be at the Academic Success Center Auditorium on the Birmingham West Campus, but it's right there across the street from East Campus. It's, the building faces, in one side of it, faces Wilson Road, but you have to enter it from the campus side. You can't, there's no parking there. You can't access parking Wilson Road. You have to turn into campus to get there. That will be from 1 to 3 p.m. next Tuesday, next Wednesday, October 9th, 1 week from tomorrow. Then the next day, Thursday, October 10th, which is our final exam date, isn't it? I believe so. That will be in the faculty cafeteria. That's right next to the cafeteria. It's called the faculty staff dining room, and that will be on this campus from 1 to 3. Scholarship Summit Fall 2019 participants include Alabama A&M, Alabama State, University of Alabama Huntsville, Birmingham Southern, Jacksonville State, Tuskegee, Miles, University of Alabama Tuscaloosa, UAB, Mercer from over in Georgia, Sanford from here in Birmingham, University of West Alabama, North Alabama, Mississippi State, okay, then University of South Alabama. Success is where preparation and opportunity meet. That's sponsored by the Career Services, Counseling Services, and the Space Center. Okay. So plan to try to get to one of those if you're coming up on graduation pretty soon. And then the NCAS, that's NASA's Community College Aerospace Scholars Program, will be accepting applications through October 16th. If you want more information, how to access an application, any of that kind of stuff, I have the information here. You're welcome to look at it. I think I got everybody here who came in late. All right, now let's talk about this class. After class on Thursday, I tried my best to get in touch with Jerry Tracy, and I failed. And if he has called back, I haven't been able to find out how he's done so, okay? I had intended to try again on Friday, but my work study student didn't come in. We had a department and chairs meeting, and I had to work on the spring schedule, and that ate up my day. I didn't get a chance to get back in touch with him. Though I probably wouldn't have been successful then either, because I was gone by the time he usually gets into work. So I was going to try again yesterday. I knew he wouldn't be in the morning, so again, my work study student was sick, so I had to finish up what we were working on, and I was here till after 6 last night getting spring schedule finished. And I meant to call in the afternoon, and I was so bogged down with that, I didn't get it done. So I emailed him, and I checked several times. So far, he hasn't emailed back. But that's not all that unusual, because he's not particularly great at emails either. This is Maurice, right? Okay. So I'm going to keep checking, and before you leave today, ask me again, and I'm going to check and see if he's emailed this afternoon. He usually doesn't get into work until sometime about the time we're leaving campus, because he works afternoon, evening, and into the whatever the late news is. So he's there all afternoon and evening on Monday through Friday. So he doesn't usually come in until after this time of day. So you may not see that email until he gets in.
Can you tell him when you're telling our break?
What's that?
Can you tell him our break?
I can try, but usually he's not in that soon, but I will try and I will check the email too. But I thought I might catch him. That's why after class last time, it was before the broadcast and stuff, still couldn't get him. And I tried to get in touch with someone else to get in touch with him, and nothing worked. Nothing worked. Usually someone will answer the phone and they'll get a message to him, but they weren't manning the switchboard. So I'll try again. Hopefully it will be Thursday, and hopefully I'll know before you leave today. But that's a hope, and that's about all it is right now. Okay. But there is a possibility it could be Tuesday of next week. I hope it's not Thursday of next week, but it could even be Thursday of next week. We'll just have to arrange things otherwise. All right, any questions? Excuse me. All right. Where we left off last time was chapter 24, page 613 on my book. I don't know what it is in your book. And it's freshwater as a resource. And that's where we're beginning today. Any questions? Oh, wait, before I get into that. You do know that the chapter 23 test is the last 30 minutes of today. However soon that gets here, okay, whatever that would be. Now, if things don't pan out for the field trip, we got to do something to use the rest of our time. Well, one thing, we got the lab for chapter 24, and if we don't go to the field trip on Thursday, we'll plan to do that on Thursday. But that's just not going to take you that long to do, because it's pretty reasonable lab. There's some things to do in it, and it'll take some time, but it probably isn't going to take a full 2 hours. So, as a contingency, what do you feel about those who choose to, want to, report on your research papers, and that will be a bonus lab for anyone who reports on research papers. Seem like something you might want to do? So,
run that by me one more again.
What's that?
Run that by me one more again.
Okay.
I can't hear you back.
I'm sorry.
Just run it by me.
Okay. The if we don't get to go to the channel 13, if for some reason it all falls apart, we got time. Okay, this will be the second field trip we would have missed. Okay, so those were into the planning of the schedule. So what we'll need to do is something to fill the time Thursday and also the time on Tuesday. Okay, next Thursday is going to be the final exam. Next Tuesday, I will be returning all these papers to you. So that's another thing, folks. And this is a very legitimate use of time that we have. If any of you are behind a test or a lab, we'll be finishing early today, I'm pretty sure. Get your your labs and tests completed. Okay? You can do it today. And if we don't go on the field trip, that will be an opportunity for Thursday as well. And even next Tuesday, if we don't go on the field trip at all. I'm hoping we'll be going Thursday. And if we do go Thursday, that will occupy just about all the day. Okay? So, we go Thursday, the field trip will be it. The following Tuesday, we'll have the lab for this chapter, and then that would be possible time for reports on research papers. So that's what I was talking about. We've got some time that we need to fill, and anyone that wants to report on a research paper that you did, or anything else, if you found something else that was of great interest to you, then you can earn an extra bonus slab for that. Because you would have had an extra bonus slab for the other field trip, since we didn't get to, this will be the other extra bonus slab. So, depends on when the field trip is going to be, if it's going to be, but we either got 1 or 2 days that we'll have plenty of time for reports on research papers. Okay? So, that will be part of either Thursdays, if we don't go on the field trip then, or Tuesdays, if we don't go on the field trip then. The following Thursday, unless that's a field trip, then everything will be juggled around. I'll let you know. But before you leave today, let me check and see if Terry Tracy has responded to my email. Okay.
If they do a bonus,
Yeah.
does that take place or something that they
Yeah.
go along?
Yeah, that you get to drop a lower lab. Yeah. So you'll get 25 points for the bonus lab, just presenting your results. Okay. What you learned in the research paper. Okay. So last 30 minutes today will be the test on chapter 23. Let's get going on chapter 24. Unless there's questions. Any questions? All right. Fresh water as a resource, okay? I would say a vital resource. Fresh water is required for life processes and modern industrial society. Now, life processes, all life processes. Plants, animals, humans, all life processes depends on fresh water. Except perhaps the things that live in the seas, okay, the ocean. They don't need fresh water, okay? But the rest of us do, okay? Required for life processes for all who live on land and for modern industrial society. In fact, the average U.S. usage, this is amazing, is 570 liters per person per day. Now, do any of you have an idea what a liter is?
Less than a gallon.
Second.
A little less than a gallon.
A lot less than a gallon. A little more than a quart. Okay? I see a bottle there. What is the amount in that bottle? Excuse me. What you got? What's that? 500 milliliters or something like that? 591 milliliters. That's about a pint, isn't it? Is that 1 pint?
Yeah, no, it's 1.25.
1.25 pints. Okay. So, again, 0.91, 591. So a little bit more than twice that. I mean, a little bit less than twice that would be 1 liter. Think of a quart of milk. If you poured a liter into that quart bottle, it would overflow just a little bit. Okay? So, 4 liters is more than a gallon. So divide this by 4, and you get 140, let's call it 143 or so gallons. 143 gallons of water a person a day? I don't drink that much. Do you? Okay. No, this isn't just drinking. Okay?
So a liter is more than a gallon?
A liter is more than a quart. So divide this by 4 and you get how many gallons? Okay. Now, 40% of that is agriculture. Now you might say, but I don't do agriculture. You consume agricultural products. Okay? The bread you eat, the drinks you drink, the meat that you eat, all that water is essential for producing every bit of that. 40% is for the production of electricity. Okay? Just about all of our electricity, especially in the old days, was boiling steam turbines, okay? Using water to produce steam to run through the turbines to produce our electricity. That's the coal-fired power plants, the natural gas-fired power plants, the fuel, any kind of fuel oil power plant. Those all are producing steam. Now, the things that aren't are hydroelectric, but they're also using water, okay, to turn the water turbines, okay. Recently, since most of these slides have been put together, we've got more and more solar, so still to a limited extent, and wind turbines, okay? But still very small, okay? Most of it is still here, okay? 10% industrial, okay? The paper that you're writing on or reading from, the inks, and all that, water is used in all those industrial processes. In packaging food, in, well, just everything. Water is, and it's fresh water, used in all this. Most of the supply comes from surface water. Now, what do we mean by surface water? Rivers, lakes, streams, reservoirs, okay? Now, the problem with surface water, you get more sediments that you have to filter out, and that's why if you go down 280 toward the summit, in Birmingham, you don't want Birmingham, okay? But anyway, you go down 280 toward the summit, you pass a big filtering plant on the right as you're going to the summit. There's pulling out those sediments. They have to treat it for bacteria. There's also pollutants. They have to treat to make sure they rid as much of those pollutants as possible. And all the surface water depends on precipitation, which, as you have been noticing lately, we don't have much. It's not recently, and not projected for a while yet, is there?
Maybe
When?
A chance this weekend, I think.
This weekend, maybe. We can hope. Okay? So, surface water. Now, more than 40% comes from groundwater. Now, what do we mean by groundwater? That we pumped up from the ground. Now, I'm sort of surprised there's that big a percentage, but now the groundwater is relative free of the bacteria, mostly free of the suspended particles, but it requires energy to pump it to the surface. Okay? And in the old days, we used windmills for that. We don't much anymore. Perhaps we should. Okay? I remember when my father and uncle bought the farms in Georgia, where I grew up, when I was 4 years old. The part of the farm that had the house on it, it was probably 75 acres or something like that. Not a big part of the farm, but it had a windmill that had been used to provide water for the cattle. They quit using the electric pump yet. I wish, we don't own that land anymore, but if we had, I wish windmills were broke down frequently, so they weren't reliable. But I wish they were. So we're using a lot of energy to pump groundwater to the surface. I think I also told you, let's go back to this agriculture part. The irrigation systems they use for agriculture, and they didn't used to do that much here in the southeast because we got plenty of rainfall. But agriculture has become such a big business, they can't afford to have a drought, so they have to have the irrigation, they think. And by the way, I saw this up here the other day. I forgot to erase it. I'm afraid it's been there too long and dried out. But while that erases, but this doesn't. I'll have to get that later. Someone remind me at the end of the class to get that cleaned. Oh, that's not bad. Okay. Most of that agriculture irrigation water is pumped. Not all. Out in California, they use a lot of surface water for that. But the farms around us in Georgia are all pumping. That's why the water table is sinking. We have a real big propensity to use more than is being supplied of just about everything, including water. Now, what about seawater? 70% of the Earth's surface is completely covered with seawater. Average depth of 3,800 meters. Now, I don't know if y'all think in terms of meters. That would be 3.8 kilometers, okay? And a kilometer is about 6/10 of a mile. 6/10 of a mile. So, I don't know. About I'm in trouble with my math now. About 2 3/4 miles deep. Average depth, something along that nature. Okay. 30% of the Earth is dry land with an average altitude of 830 meters. Now that's average. Mountains, of course, are higher, but the average altitude. Look how deep the average sea is from water level, and how high average land. You could take Mount Everest, the tallest mountain in the world, and drop them, if you can get it, drop it in several places in the ocean and never see it again. Our oceans are that deep, that major. And think about how much volume of water that is. An average of this, 70% of the Earth's surface. Amazing. And most of the ocean is still unexplored, basically not understood. Period. We have very little knowledge or understanding of what's in our oceans. Now, let's back off for a moment here. Israel is probably the major country I've heard is doing much of this. But some other, in places in the U.S., I'm sure are beginning to. They're actually trying to extract fresh water from seawater. I think Reuben was asking me about this the other day, reverse osmosis and things like that. There are processes for doing it. It doesn't all involve boiling water and condensing it, distilling it out. It's a very heat-intensive process. They've got some better ways of doing it. Ethan, right?
Yes.
Okay. Well, guess what? I already had you marked here. I put CJ in your place. Okay.
Did you say heat intensive?
Heat intensive, absolutely. Energy intensive to distill water. But some of the other processes are a lot more efficient. So if you say, do we have enough water? Well, we got plenty of water, but we just can't consume seawater. Are all of you aware why we can't drink seawater? Any ideas? Huh? Salty, yeah. And what it is, it would not quench your thirst. Because what you're drinking water, when you're thirsty, what is happening, the liquid, the water inside you, and by the way, you are probably pretty close to 70% water yourself. I'm not sure exact percentage. Check with a biologist, you could probably find out. We are mostly water, and most living things are, okay? If that liquid in our fluid systems gets salt buildup, okay? That's why we get thirsty, to neutralize that and flush some of the salts out, okay? Y'all understand that process. Okay? If you were to drink seawater, that basically is more concentrated with salts than what our body's trying to expel. So it wouldn't. Okay? So you would just get thirstier and thirstier until you probably pop. Okay? Because you wouldn't be able to neutralize the salts and get rid of them. You would actually be putting more salts in. So you have to be able to desalinate the seawater. And it is an energy-intensive process. Okay. So let's look at the salt water, the oceans and the seas. Now, what is an ocean? You've got a good idea, probably. It's a continuous body of water covering the Earth's surface. Okay? We have three principal regions we call oceans. Now, some others will split it up into other areas, but these are the three principal regions. Okay? Get my handy-dandy visual aid. We've talked about this several times. There is the Atlantic Ocean, going from somewhere way up north here, all the way down past South America, Central, and Africa, down in here. Some maps will list North Atlantic and South Atlantic Ocean. There is no dividing line. That's the Atlantic Ocean. Okay? It's the second largest ocean. Is it getting bigger or smaller? It's bigger. Very, very, very small amount. But remember, we have the diverging plates in the middle of the Atlantic Ocean. So it is growing ever so slowly. Then we have the Pacific Ocean, okay? The big one, okay? That's the largest, with the greatest depth. There are places in the Pacific, I can't remember for certain, but it seems like more than 5 miles deep. That is deep. Now, just sort of guessing on that number there. And then the Indian Ocean is considered an ocean, and that's a pretty good sized ocean too, but it's smallest in surface area of the 3 major oceans. Okay? And still a pretty good sized body of water. Now, what is it that basically is the difference in an ocean and a sea? An ocean is a large continuous body of salt water covering the Earth's surface. A sea, on the other hand, is a smaller region distinguished by special characteristics. And they don't say what those are. Basically, they're pretty much enclosed. Not completely, but coming close to being enclosed. For instance, here's the Mediterranean Sea. Okay? A pretty good sized sea. Now, it doesn't look all that impressive here, but when you think about at the closest points, I'm not even sure you can see land on the other side. I haven't been to Gibraltar. That would be the closest. I think maybe you can see across it. You can? Okay. But in most of the rest of this, you have a ways to go before you see land on the other side. So that's a pretty good sized sea. Okay? The Gulf of Mexico is considered a sea. Almost enclosed, not quite. No sea is. But that's the Gulf of Mexico. Again, pretty well defined. Okay? The Caribbean Sea, okay, is down here. Now, it's enclosed, you might say, by a bunch of islands, but that's the Caribbean Sea down here. Now, there's some other seas within the oceans, but just by name. Here's one that calls the Sargasso Sea. The reason they name it that is it was a good fishing area at one time. Not sure it is all that good anymore. So that's not one of the seas we're talking about. Other seas, if you go back to the Mediterranean, there's the Black Sea. Here's the Caspian Sea. Those are almost completely enclosed. You have to have inlets and outlets to form the seas, but they're there. Here's the Red Sea of biblical fame. Here's another Gulf, the Gulf of Aden. Here's the Persian Gulf, okay? and the Gulf of Oman here. Both would be classified seas. Now, the Arabian Sea is the part close to the Arabian Peninsula. However, it's not really enclosed very much, but this part here would sometimes be considered a sea. I consider it part of the Indian Ocean, but they do call it that. And by the way, in the Mediterranean, on the backside of Italy, the side near the heel and the backside of the boot, that's called the Adriatic Sea, named after the Emperor Hadrian. They just dropped the H and made it Adriatic Sea. And then also in here around Greece, you have the Aegean Sea. That was an old name, I think, for Greece. And you have some smaller seas there, but that's really all part of the Mediterranean. So you can have other local names, but they are really part of the go up to Northern Europe, the Baltic Sea, enclosed almost by Scandinavia. Denmark here, Sweden here. Again, they're pretty close, but I don't know if you can actually see across and see them. Here's the Gulf of, I can't quite read that, Bothnia or something like that. Here's the North Sea, almost enclosed by England and Scandinavia, Northern Europe. You have seas up here, various names. No one ever goes there. There's a cold. Hudson Bay would be considered a sea up here in Canada. Baffin Bay up here. There are other seas around. This Gulf of Alaska I count as part of the Pacific Ocean. Okay, but here is the Bering Sea, and that is almost enclosed by this island chain. Those are the Aleutian Island. Remember, we talked about the chain islands where the plates meet. That would be, that closes in the Bering Sea. Here's the Sea of something or another, Okhotsk or something like that. Russian, which has too many there, so consonants in it, okay? And there's various other seas up here. Somewhere up here, they say here Arctic Ocean. It's really more of a sea, okay? So different maps will list it different ways, okay? So you see you have quite a few seas around. Sea of Japan, closed here by the Japanese island chain, and Asia on the other side. The South China Sea, closed by the, I can't know how to pronounce that, Ryukyu Islands, that closes in the South China Sea. Above that is the Yellow Sea. So you have a variety of seas. And here's, this is East China Sea. Here's South China Sea down here. Near Vietnam. That was famous here in Vietnam, here, South China Sea. So you have a variety of seas like this, lots of different names, plenty to go from. If you get down here and there, South America, you have a few other seas. Here's Weddell Sea here. Ross Sea, I couldn't find the name. It's right next to the Ross Ice Shelf, and that Ross Ice Shelf is melting fairly quickly, filling up the Ross Sea. Not completely enclosed, but pretty much identified. They call this the Tasman Sea, in between New Zealand, Australia, and the island of Tasmania here. So that's the Tasman Sea. Coral Sea here of World War II fame. Quite a major battle, sea battle, occurred there. Basically where the Japanese fleet was decimated. We pretty much began to wipe out there. They had been pretty much had the upper hand the first part of the war. I think, if my history is right, it may not be the Coral Sea, the Battle of Coral Sea was sort of the turning point for us. We were very successful in wiping out much of their naval fleet. And that's basically how they had to go. They had sent troops over to China and stuff, but they were trying to get to Australia. I think that's why the Battle of Coral Sea was pretty significant. But you see lots of seas on there. Okay, they just mentioned a few here. They're bounded by land on some sides. Okay, sometimes almost enclosed, but never quite. So that's what makes a sea a sea. And here is in the map. I've been showing you the globe, and you'll find this as a figure in your book. Sort of the Pacific Ocean here and here. They usually cut it down the middle because it's just water on either side pretty much. Indian Ocean here, Atlantic Ocean here. Pacific, of course, the largest, Atlantic second, Indian third. Okay, and then various seas, and they list several of them here. Hard to see them all probably from where you're sitting, or even Ryan as he's coming in close, but anyone else come in and say, oh, I saw you, but I forgot to stop and mark you. Lexi's here. Anyone else who came in that I did not mark? Okay. All right. Find it in your text. This, by the way, is, haven't been turning pages. Let me go back a slide or two. This one, when we talk about how much water we use, we certainly never suspected we use anywhere close to 40, 150 gallons a day. No way, we would think. But here's a table 24.1, shows the average individual freshwater usage, not talking about agriculture, electricity, and industrial, just what we're using in our houses. Toilet flushing accounts for almost a quarter of it, clothes washing more than a fifth of it, showering about a sixth of it, just running the faucets for various other things like washing dishes, drinking water, that kind of stuff, 15.7%, almost a sixth, and leaks and other, as in maybe watering plants and things like this, almost a fifth. Okay, so yeah, quite a bit of water usage besides drinking. So, or even cooking. Cooking would probably fall under the faucet use. Okay, should have mentioned that as that. Now, they have a great blurb here, especially for any of you who may be interested in it, on pages 6, 15, 14, and 15 on water quality and wastewater treatment. And it goes over both pages and has several good figures, 2 good figures, and quite a bit of verbiage about water quality and wastewater treatment. And I have a real tendency to ask if you would find drinking treated wastewater an acceptable thing to do. I see a few heads shaking. Huh? What was that?
That's what we're drinking, right?
That is exactly what we're drinking. Everything was at one time wastewater, because we're not really manufacturing any new water anytime. I have actually heard it said, if you go far enough back in history, you probably have at least one drop of water in your body that would have been in, and you could just, maybe I should say molecule of water, that would have been, say, in George Washington's body, or pick someone else who lived in the general thing. It's just, we're always recycling water. We are drinking some previous wastewater right now, and it's been wastewater many times over and over and over again. Now, it's probably pretty gross to think about it that way, but that's exactly what we do. The earth itself filters water as it goes into the groundwater, and that's relatively free of bacteria and suspended particles. because it's filtered through all that. Remember our well at the farm, I think it was about 250 feet deep. That filtered through 250 feet of soil. And after the topsoil, there was very little trash in there. It's mostly just filtering from then on. So that's why it's good, really clean artesian water. That we're drinking out of lakes, that's another issue. And that's why I've mentioned it here. Water quality and wastewater treatment, but any water treatment, okay? Lake Purdy is where Birmingham gets most of its water, right? Isn't that on the Cahaba River? Or one of the rivers up north of us, right? And it's there, and we get our water from there. And then our wastewater ducts back into some river somewhere. Now, we do treat it, yeah, and try to clean it up some, but it goes on downstream, and then somebody else has a dam somewhere further downstream, and they're using that same water over again. And then they're dumping it, and it goes on down. Ultimately, it gets back to the ocean, then evaporates and comes back in precipitation again, okay, to replenish the other. But we're recycling water and recycling water and recycling water. Okay, sorry. The figures on page 616 show irrigation systems. Well, the one at the top is a filtering bed for a city wastewater water treatment facility. And then on the lower picture there, figure 2410, is an irrigation situation, I think. Okay. Now that gets us into where we were here. I was going to tell you where we were in the book. This figure that you see here, much bigger and easier to read on page 618. Okay? Believe me, you'll see it. You'll need to see it again when we do the lab, because you'll be getting a lot of your information off of figures like that. Okay. So, oceans and seas, the primary source of most of our salt water. So, what's the nature of seawater? This is the topic or subtopic begun on page 618. Well, what makes seawater seawater is someone says salt, salinity, that's the salt content. It's the mass of salt dissolved per kilogram of seawater. The mass of salt per kilogram of seawater. Generally, now this is a gross generalization, it does not change appreciably with changes in water temperature. And there's a couple of reasons for that. The amount of salt that water can dissolve depends on its temperature. But see, the seawater temperature doesn't really change. If you're boiling water, yeah, you can dissolve a lot more salt in something close. None of our seawater is anywhere close to boiling, okay? But then, too, you could have more salts in them, but then it also evaporates. So it all pretty much works out. Does not change appreciably. I would put appreciably with changes in water temperature. Now, this statement here is wrong. Okay? The numbers are okay, it's the symbol that's wrong. This says percent. It averages, they're saying salinity 35% within a 32 to 36% range. That's not percent. This is per thousand. Cent means 100. Percent is out of 100. This is out of 1,000. 35 parts per thousand. So for that to be written correctly, and I think it's correct in your text, you'll see the symbol. It's at the last paragraph on page 618, and then moving into 619. Okay. And you'll see that thing. So this should be, let me get my blue pen up. I don't know which color blue would be better. This should be per thousand, not percent. Okay? So there should be an extra little zero there. You don't usually see that, but this is what they're talking about. If they had said percent, that would be 3.5% within a 3.2 to 3.6%. Why didn't they say it that way if they were going to use the percent symbol? But they used the 35, but then they didn't have the per thousand. Okay. So did want to make sure you understood that. Okay. Now, what creates this ranges here? Concentration is increased by evaporation. And again, the warmer the water is, the more it evaporates. But also by ice formation. So up in the cold areas where you don't have as much evaporation, you still have ice water freezing. And guess what? The ice doesn't freeze. I mean, the salt doesn't freeze. Only the water freezes. Okay. Now, I bet you some of that water will taste salty because it captures some sodium chloride crystals in the frozen water, but that isn't what's freezing. It's the water that's freezing. Okay? So you see, that's why you increase concentrations in cold water and in hot water. It's decreased by heavy precipitation, okay, which would include the major hurricanes and storms like this that have just dumped tons and tons of water, but done it out in the ocean. In those areas, the salinity goes down this way. Okay? Now, ice melting. Sadly, we've got a lot of that going on now. So our water's up near the poles. Near Greenland and Antarctica, in those areas, the salinity is going down because you have an unusual amount of ice melt. And then river inflows. I just was hearing on the news sometime last week that much of the Gulf of Mexico has been declared some type of disaster area because of the flooding that we had in the Midwest all spring. Remember, just tons and tons of places just getting so much water, so much flood. The Mississippi was dumping enormous quantities of water into the Gulf. And then we've had a couple of hurricanes and tropical storms and depressions since then. And much of the good fishing down here, the fish have moved further away to get saltier water because they're saltwater fish. They cannot live where the salts are not high enough. So the fishing, and much of the fishing in these areas here where a lot of people depend on fishing, the fish have moved further away than most of their boats can handle. They can't go that far out. So it's an economic, I guess, disaster area or something like that. They had a name for it. I don't remember what it was. Okay. Now, so river inflow and also heavy precipitation as in the tropical systems. The proportion of ions is relatively constant, okay? Meaning what proportion is which ion. That's what they're talking about here. And you do have a table in your book that lists some of those. Now these are percents of the ions dissolved in seawater. Okay. Now probably what you would assume the most prevalent would be salt, sodium chloride. And if you look at it, the sodium ion, almost 31%, chloride ions almost 55%. Well, why would that be? Well, part of the reason is chlorine is a heavier ion than sodium. It's several elements in between. So chlorine is around 35.45, whereas sodium is 23, basically. So yeah, this is by weight. So there would always be, for an equal number of chloride and sodium ions, the chlorine ions are greater by weight, even when you have the same number. Okay, now this much difference probably isn't accounted for by that, but that's what attributes to part of it. But that adds up to about 85%. There's plenty of other salts besides sodium chloride salt in the seawater. Sulfates, well, let me see. There used to be another error here, and I'm trying to see if there is one now. They may have gotten it corrected in this edition. I think they did. Okay, let's see if this is also showing up here. Here is where the error is, and it's just minor things. Okay. So rather than looking at the book, sodium and chlorine, sodium ion, positive ion, chlorine, the negative ion, they add up to about 85, 86%, okay, of the salts that are in seawater is our regular table salt. But you see, you also have sulfate ion, which is another negative ion, and that's almost 8%. Magnesium ion, that's a +2. Sulfate is a -2. That's almost 4%. Calcium ion, whereas everywhere on the surface, calcium always supersedes magnesium, but in the seawater, the magnesium is greater. Calcium is only about 1%. Potassium, this is one of the errors. That's a plus. Potassium is a plus ion, not a negative ion. So that should be a plus there. This looks like this is more dark, so let me get my black pen here. And that's going to be a plus right there. In your book, it's correct. It's a K plus, okay? About 1%, short behind calcium. Bicarbonate, and it's sort of interesting they do a bicarbonate ion. And here's the other error. It's just a minor one. This should be a superscript minus. That's the charge on the entire ion, not anything to do with the 3 down here. That's HCO3. The 3 means how many oxygens. It's a single minus sign. So that should be elevated or superscripted up to here. Okay? I can't get this to work. Okay, that's where the minus sign should be, not down there. Okay. I can't get it to work. It's way too small. This is a big fat pen. Okay, the minus sign up there. A bicarbonate ion. Okay, and that's less than half of 8%. Bromide, another negative ion, and that's 0.2%. Okay, that one's 4 tenths. Total here, we've accounted for all but about 11 hundredths of a percent. So got most of it covered. Lots of other things make up the other small percentage. Okay, so those are the ions present, and that's what they mean. The proportion of the ions here are relatively constant. That's just what you got there. Now, salt water, as all water, also contains dissolved gases. How do you know that's true? Fish live, okay? The sea plants live. They've got to have dissolved gases to live. You know, the fish have their gills. That's where they get the oxygen out of the seawater. So the nitrogen and oxygen is near the surface, and there's a fairly large amount of CO2. Not nearly as much as there is nitrogen and oxygen, but there is a fairly large amount of CO2. Now, nitrogen and oxygen are fairly light compared to CO2, so the CO2 will go deeper, and also because the fish breathe in, just like we do, oxygen and breathe out carbon dioxide. Plants that are in there. There's maybe a few plants that photosynthesize right near the surface, but most of the plants are same as us, breathing in oxygen and breathing out CO2. So the deeper you go, the higher and the higher the concentrations of CO2, and the oxygen especially gets less concentrated as you go deeper into the water. Nitrogen is just there because most of the air is nitrogen. Something close to 80%, like 78% of the air in this room is nitrogen, not oxygen, nitrogen. We breathe it in and breathe it right back out. We don't use it at all. Now, this is a completely different subject. Some plants are able to use the nitrogen in the air to make proteins. Those are your legumes, your peas, your beans, your peanuts, things like that. They have little bacteria called rhizobia that, this is in the soil, not in water, that are able to extract the nitrogen and combine it chemically to become nitrate, which the plants use. And they attach themselves to the roots of the plants. It's a very symbiotic relationship. They get their nutrition from the plants, and the plants get their nitrogen source from the bacteria. There are some fungi that do the same thing for trees. Those are called mycorrhizae. They pull out beneficial things for trees, tree roots, and in exchange get their carbs, their sugars and stuff that they need to live. But that's beside the point. There are things in the ocean that do that too. But by and large, more of them are using oxygen and emitting carbon dioxide, just like we do. Okay, let me get my markings off the screen now. Okay, so to get back to our, not percentages, I'll erase them too, parts per thousand, you have 35 grams of salt in 1 liter of salt water. That's what it says here. The mass of salt dissolved per kilogram of seawater. Kilogram is 1,000 grams. So it's 35 grams per 1,000 grams. So that is 35 per 1,000, not percent. 3.5%, 35 per 1,000. Okay? So if you subtracted out the 35 grams of salt, then you only have 965 grams of pure water. But it's never done that way. It's all together. Now, do any of you prefer using sea salt to other salt? I do too. In fact, I think it tastes better. That goes back to this table here. You see, with sea salt, you're getting, 85% of that is sodium chloride, okay? But the rest of it are other salts that we really need. Sulfates to some extent. Magnesium for sure, yes. Calcium for sure, yes. Potassium for sure, yes. Bicarbonates, we need some. Bromines are so little, I don't know what we use it for, but it could be just about anything. Okay. So, in case you're ever wondering what's the difference in sea salts, you get lots of other minerals beside just sodium chloride. Sodium you have very little use for. Chlorine you have very little use for. Okay, you got it all over in your body, so you got plenty, so you don't need that. The others you do, much more so. All right, now here we hit some of the, and by the way, there is an example here in your text, example 24.3 on page 619. How many grams of salt could be obtained by completely evaporating a plastic 5-gallon bucket holding 19 liters of seawater with a density of 1.03 grams per cubic centimeter and a salinity of 31, and there they use the right thing, per 1,000. That's just an exercise in manipulating numbers. There's nothing you need to know there. It just is how to manipulate numbers. So it might be worth looking at to see how they did it, but don't get too bent out of shape over it. Okay. Before we get to movement of seawater, there's again a great blurb. This is really a good one on estuary pollution. Does anyone know what an estuary is? this is a really gross and not very scientific definition. If you remember what a delta was, that's where land settles out of water and fills in and forms in a bay. Well, the estuary would be the leftover water. What it forms there, it's the water around where river or stream or something like that dumps into the sea. It's not going to be salt water yet. It's not going to be fresh water. It's sort of brackish. And when we talk about estuary pollution, we're talking about the pollution that happens to those areas near the shore where water has dumped in. Now, this is really a good read, so please read it. They talk about several of the things that mess up your estuaries. Have any of you ever heard the term the red tide? And I'm not talking about the crimson tide, no, the red tide. Second? No, not that either, okay? And those two are not related, by the way, okay. Second? Very good. Who's saying that? All right, good. That's the place I've heard about it the most is Potomac, where the Potomac River around Washington, D.C. What do you call that? Second? Potomac River, near Washington, D.C.
Yeah.
What is?
The bay?
Yeah, the bay, Chesapeake Bay. That's what I was trying to think of. Chesapeake Bay. They've had it really bad, but many others have too. And this is exactly what he said, algae and bacteria and other things that just, what they do, they suck all the oxygen out of the water, and as they proliferate, and then the fish die because there's not enough oxygen for them. And they get pretty sick too, because these are not very positive things. And if you'll read through there, you'll see they talk about, I can't pronounce it, Escherichia coli, bacteria commonly found in the intestines of humans and other warm-blooded animals. Much easier to call it E. coli, which you probably heard of. It's all over in, where it's in the estuaries, you really don't want to eat the fish caught there because they could be contaminated. And it's just a good read. So by all means, pay attention to that. All right, now we've gotten to movement of seawater. It's sort of hard to believe, but with all the water coming onto land and moving back to the oceans, the huge oceans here, here, and here, that you have the seas where they are and everything else, it takes a complete mixing of the Earth's seawater, happens about every 2,000 years. That's 2 millennia, okay? It's happened about 1.5 million times in the 3 billion years that we've known the Earth has been pretty much in existence, okay? Now, what in the world is doing all this mixing? It would look like the water would just sit there and stay, and the Atlantic would stay in the Atlantic, and the Indian would stay there. No, it doesn't. There's 2 types of motion. One is primarily a surface motion, that we call the waves, produced by disturbances, mostly caused by wind blowing over that surface of the ocean for long periods of time, over time, and that moves the waves. So that mixes the top part of the waters pretty thoroughly and keeps them moving, okay? Now, it doesn't have to be wind disturbance. Anytime you have an earthquake near the water, then you have tidal waves moving in. That moves even more volumes of water for long, long distances, but they don't happen that frequently. So your air waves will probably, waves induced by wind, will probably do more total mixing. But then we have the currents. This is movement of water from one place to another. Usually these are deep. Now they can be near the surface too, but usually they're pretty deep. You talk about not understanding things. What causes these? What starts them? What keeps them moving? We have a very lousy understanding. Okay? The currents. And they move in enormous amounts of water. Okay? It's like huge rivers within the oceans, okay, that carry water. And we'll talk about several of these currents coming up now. Well, let's first talk about the waves. This is the simplest structure, the moving crest and the troughs. Okay? Now here's a couple of characteristics of waves, things that we measure. The distance from one crest to another crest, or the bottom of one trough to the bottom of the next trough, that's called the wave length. Okay? Now that sounds like something you were talking about, electromagnetic radiation. We do, but it's a different thing there. This is the wavelength here. The distance length is trough, crest to crest. The wave height is from trough to crest. That's another distance measurement, and that's the wave height. Okay. All right. So wave height is the vertical distance from the trough to the crest, right here. Okay, trough to crest. And wavelength is the horizontal distance between two consecutive crests or troughs or whatever. They would be the same. So those are both length measurements. The wave period, though, is a time measurement. Okay? And that will be the time between the passage of two successive crests. Because the water doesn't just stand up here and stay there, the water is moving. So at some point, this wave was back here. And as the wave moves, it moves here. So the time that it took to get from here to here, that is the wave period. The time between the passage of two successive crests. So actually what we measure is we set up our measurement here. We measure this crest when it went by, start the stopwatch, and then when the next crest comes, stop it. That would be the time interval between the two crests. Okay? Wave period. Time of passage between two successive crests. Now, these ocean waves, this is bigger than the waves that you really are talking about, say, on a swimming pool or a lake or something like that. The characteristic depends on three factors. One of those is certainly the wind speed. Now, the Pacific Ocean, where do you think it got its name? It was in general pretty much the pacified ocean. It didn't have the major storms that the Atlantic was known for. Now it has major storms, but it's basically a much quieter, stiller body of water generally than the Atlantic Ocean is. I've been on both. Were you on both?
Mm-hmm.
Okay. Did you find the Atlantic was rougher generally?
Yeah.
Yeah. I just been crossed the Atlantic just once. Well, crossed and then went back. And both times, I was trying to think if I actually got pretty major seasick or not. I don't think I did too badly, but I knew of people who just about any time they went out to the Atlantic really got seasick badly. A friend of my brother's finally had to take a medical out.
Drowning.
Because he just was chronic seasick. And he hated to go, and his command hated him to go. He was a really good sailor, but he just did not handle it. He was in the Atlantic. Now, I've been in the Pacific when there's been storms too, but generally that's a much calmer body of water. Okay? But they still have places where they have high wind speeds. Now, as opposed to this, some of the greatest surfing in the world is in Hawaii and places like this in the Pacific, but that's probably more due to the shape of that particular bay and the fact that you've had wind blowing. We'll get to that in a minute, over a longer period of time. There's also some great places in Australia and several other places in the world. Probably we haven't even discovered yet. But wind speed is one feature there. How fast is the wind blowing? The faster it's blowing, the more it's able to move the water. Think of this. Speed is related to kinetic energy. Energy is the ability to do work, which would be moving water. Now, the length of time that the wind blows, this is where the Pacific really gains traction, you might say. Because if you imagine, look how big the Pacific Ocean is. If that wind is blowing fairly constantly in the same direction for long periods of time, it can really build up some waves. Even though it's not stormy, it can still build up some waves. The length of time that the wind blows. And then the fetch, this is length of time that it blows. The fetch is the distance the wind blows across the open ocean. And there again, in the Pacific, look at the distances involved here. Huge amounts of distances, okay, that wind is blowing generally in the same direction. So the length of time that the wind blows and the distance over which that wind blows. Now, what you get out of all this is a fairly complicated mixture of wavelengths and wave heights. Okay? If you've had wind blowing for several days, and we're going to get to this in a minute, right down here. If you've had a fairly constant wind over a long period of time, that creates the swells. Okay, we're going to get to that in a minute. The bigger waves, longer, everything's bigger about it. But then the wind changes sometime or another. They're going to immediately change those swells. They're going to keep going the way they've been going, but it makes the smaller waves go in a different direction. So that's why they say it's a complicated mixture of wavelengths and heights generated. The smaller waves will dissipate from friction within the water. Can you believe that water has friction? Have you ever jumped into a swimming pool but didn't quite get tucked the way you meant to and landed right on the belly flop? It hurt. Okay, pretty badly. Water has a fair amount of friction. Guess what? That's why you turn a propeller, the boat moves because of that friction. Okay, but that's what keeps the boat from moving is the friction that way. So you build your boats as streamlined as possible so you minimize the friction this way and maximize your push with the propellers. Okay, yes, water has friction. The larger waves last longer, generally travel faster, and eventually coalesce into your swells. That's what I was talking about before. Those waves that have been going on for day after day after day, that will produce your swells, and then maybe your waves the wind will change and start chopping them in a different direction. You have to pay attention. The swells are basically the things that will get you more than the waves will. Cause some problem with rocking is what I'm talking about. So here we talk about the swells. They carry energy but do not transport water. Because what the swells do, think of this. I think I gave you this example before. The hose lying on the ground, and you go up and down with it. The hose stays pretty much where it is. It goes up and down some, but it comes back down the same place it is. So, same thing with swells. They go up and they come down, but they don't transport this way. The energy is transported that way, but the water itself, very little. The individual particles, the motions are circular. When they go up, they may go over here. When they come down, they come back, and they almost form a complete circle. Okay, and the diameter of that circle is the wave height. Now, this is a particularly great illustration here, but I think it does the job well enough. When, say, now remember the water is moving this way, the waves are moving this way, but the water, the actual particle of water, when it's down here, and this wave comes along, it picks it up as this moves, reaches the top here, and then as it leaves, it goes back and comes back down again. So this is what creates the motion. The diameter of that is the wave height. Okay? The individual particles, motion are circular with diameter being the wave height. Now, you get down below here, and you have some of that motion going on, but it peters out until you get, now this is the weird part, okay? Remember, this is a wavelength, horizontal distance. If you move that vertically, okay, one wavelength here, at half of a wavelength, you're going to, motion will almost stop. No motion, none of that circular motion when you're below 1/2 wavelength, okay? Down to that, the circle gets smaller and smaller until 1/2 wavelength, basically no motion at all. None of that circular motion. So basically, most of our mixing is in that top wavelength, even though the wavelength is this way. I should have said half wavelength this way. Most of the mixing is there. This down here doesn't really pay any attention to that. Not much anyway. Okay. What whitecaps are is when the top of a swell is toppled by a strong wind. So you can easily imagine swells, crests don't just sit there like this. If you have any wind at all, it's going to blow this over. And if it's a strong wind, that's what forms what we call the whitecaps. When you're out at sea, most of the time we didn't see whitecaps. So only when it was getting to be a stormy type time, you saw those, and then you didn't want to be buffeted by that too much. Okay. Now, that's what water is doing itself. When you now get land involved with it, things really get complicated. Okay? Now, these are some of what they call the shore effects. And they don't have particularly great diagrams for this. This one doesn't show refraction at all. I think a later one might. I'm trying to remember now the order of these slides. That just very little. This is a little bit better. Okay? Refraction is the shoreward sides of the wave slows and the wave front bends toward the shore. Okay? So you see the wave front is bending toward the shore here because this slows down more than it does out here. So it bends it toward the shore. Again, not a particularly great exception. But basically the word refraction means bending. Bending, refraction. The shoreward side of the wave slows, the wave front bends into the shore. Now, let's get back to the earlier slides. I think that's it right there. Now, here are the swells coming in. They call them the deep water waves. I would call those the swells. Okay? And you see you have your circular motion there. That's the mixing here and then half and then less. When you get 1/2 wavelength down, basically stops. But when this comes in toward shore, now this is going happy over here, no problem at all, just rocking along. As it gets to shore, now you get the drag from the beach here, okay? underwater still, but the drag from that, and now things start bending. That's part of it. The breakers at depths less than 1 wave height, okay, the lower part slows, the top part keeps going at the same speed, and that's where you get your breakers, okay? Because the bottom is slowing, the top is going at the same speed it was before, and this was what gives you the breakers. That's part of it, okay? What the surf is the breaker formation zone. So for those people who like to surf and are good at surfing, that's where they want to be, is where the breakers. This is no fun out here at all. It's where it's breaking, that's where it is better. Is the Gulf of Mexico a great place to do surfing? No. Okay. Nothing really about the Gulf of Mexico is set up for that at all. Hawaii and perhaps some places on the Pacific coast of the U.S. may have some, and maybe some somewhere up on the Atlantic, but generally Gulf is not much, okay? But this is where your surf zone and your breakers are happening there. Now that's just part of it, okay? The lower part slows because of friction with the beach. The top part keeps moving at the same speed, so you get this breaker formations. But the other part is this. All the water that gets pushed up here has to go back. So now it's not just the beach doing this, the undercurrent, and they have their arrows backwards here in my mind, okay? This arrow should be on the bottom, this one on top. The water coming in this way is going back out that way. And that's another sort of drag on it and creating the breakers. So you have the friction of the bottom plus the returning water is pulling things backwards, okay? So that's the water transported toward the shoal by the breakers must return. That creates the undertow, the direct return of water under the breakers. Now, going back to this slide, now this one they have in there, and you just can't tell much at all from this. This is a very straight coastline, and it looks like the breakers are coming in fairly uniformly. It seems like they are breaking further closer here and further out here, and that probably has something to do with the depths under here. But without any more information, it's really hard to say. It's a pretty picture of the ocean. The one in your book may be a little bit better, but not much. Just a pretty picture of the ocean, okay? But here is what they call the longshore currents. The motion parallel to the shore, it produces rip tides upon entering the channel. And sometimes you can't see the channel, okay? Not from the surface. Now, I'm not a big beach person. I enjoy the beach, it's fine, but I've got fairly fair skin, so I don't sunburn badly, but I have a propensity, or at least my family does, for skin cancers, so I try to stay out of the sun as much as possible. So the beach is not one of my favorite places. I like it, it's fine, but I just don't like being out in the sun too long. Always wearing hats or under umbrellas or something. That's not really. But back when I was younger and I didn't go to the beach a lot, but when I did, I enjoyed what they call body surfing, right? So get out and do the breakers here and try to catch a wave and make it in the shore. Sometimes get down into the bottom of when I was doing it. But I can remember doing that for long periods of time and then going back to the beach and not recognizing a thing because of these longshore currents kept taking me down the beach, but it was so gradual I never realized it. And when I got out, I had a half-mile walk to go back and find where the rest of the folks were located. And that will do it to it. It really will. These longshore currents are motion parallel to the shore, and it's created by some of the irregularities in the underground part. And if you do have a stream under here that you can't see, some channel under there that's hauling the water out faster, but you don't realize that. That then gives you what you call rip currents. It just will literally suck you under. Now, what they were talking about before, these are also the undertow. That is it can be pretty significant. And the taller the waves, the bigger the waves, the greater the undertow. So get ready for that. But this is minor compared to the rip currents. And you don't see them, you don't know they're coming, they can suck you under. I remember one time I was never a good swimmer, and I was visiting my cousins when I was stationed in Norfolk, which if you're on the East Coast, you almost always are going to be at Norfolk for some period of time. But I had a lot of family. My mom's family, she was one of 14 kids, and a lot of them lived in the Norfolk area. So I had lots of cousins to visit there, and I was visiting one. They decided to go to the beach, so I went to the beach with them. But it was a pretty windy day, and the currents were pretty strong. Everything was pretty strong. I was not a good swimmer. I found that the more I was trying to swim in, the more I was being pulled out. I thought, this is not a good equation. What am I going to do? Fortunately, my cousin's husband was a very strong swimmer. He could see I was just losing the battle, so he came and gave me a hand. I don't know what would have happened otherwise, but I didn't want to consider the possibilities. Okay. But these are some of the shore effects and why they happen. Pardon me? Oh, I thought someone said something. I'm sorry. Oh, okay. Was there a question or a comment? Okay. Second? It's a great time for a break, I think. Okay. And by the way, a lot of these terms were here on page 623. Okay? Now, this next slide that we're going to start with when we come back, you're not going to find it in the text here. You'll have to go back to the earthquake chapter and find this, because when they went between editions, the tsunamis are now done in the earthquake chapter, not in the tidal chapter, in the earth's water chapters. So this will seem out of place, but we'll deal with it. So this is where we'll pick up when we come back. Okay, have we had any new people come in since I called? Oh, okay. Chris. All right. Anyone else? I have a few checked out, but that's not how they haven't left the room anyway. Okay. Now again, this is in a sense in place, but in another sense out of place. This isn't where tsunamis are mentioned in your text. They were talked about back in, I can't remember which chapter it was, the earthquake chapter, shaping, building the air surface. That would have been probably around 19. Yeah, 19. This is where tsunamis were mentioned then. Now we're in 24. What tsunamis are ocean waves created by earthquakes. Now, how does an earthquake create an ocean wave? Well, if the earthquake is underneath the sea and you have this enormous quaking or shaking of the underground, then that sets up a disturbance in the water, and that disturbance, the energy from there, is carried by the water. Just like it was talking about before, the swells carry energy. They don't do that much water, but they do carry energy. Okay? Lots of energy. These can be, and often are, the largest of your ocean waves. Okay? Swells and everything else. Now get some of these physical characteristics. Speeds approaching 700 kilometers per hour. That's 420 miles an hour a water wave going at that speed, get out of the way. Especially since the wavelengths can be up to 200 kilometers. That's the distance between two consecutive crests, 200 kilometers, which is about 120 miles apart. Okay? So you get hit by one. Wow, I'm glad that's over with. Here comes another. Okay? Quite a time later. The wave heights are up to half a meter in the deep ocean. That doesn't seem like a lot. That's, I'm about 2 meters tall, so half a meter is about here. Okay? A little bit longer than this. That's a cubit, in the biblical terms, 18 inches approximately. Half a meter would be a little bit longer than that. Okay? That would be in the deep ocean. Okay? This is carrying a lot of energy, but can reach 8 meters in shallow water. That would be the shoreline. Now, 8 meters, 2 meters, the ceiling's about 3 meters. So this is basically almost a 3-story building. Okay? Now, a lot of the buildings near the ocean, especially down in the Gulf, might have one floor up of garage area, so the waves can go under there, and then maybe another floor or two above that. This would swamp them all. The entire thing, 8 meters when you reach the shallow water. Now, fortunately, we don't have many tsunamis coming in the Gulf of Mexico, so you don't have to worry about that. But remember, we were talking about earthquakes. At one time, it was the largest ever recorded, and I think it may still be, one that hit somewhere in the remote areas of Alaska. No one living near there, but it was one of the most powerful earthquakes recorded since we've had seismographs to record them. And the tsunamis that made their way to the Hawaiian Islands, and this was back around the turn of the century, the last century. So Hawaiian Islands were not all that, the tourists and big buildings and stuff that they have now, but it wiped out portions of what they call the North Shore. Not many people living up there, but boy, it did a lot of damage. And it traveled over that big spatial distance. And here's Jordan, right? Okay. All right. So, they can be massive and massively destructive. I don't know how old you folks are. It doesn't seem like any time ago. It was, seems like shortly after Christmas, or right around Christmas, there was a major earthquake in Indonesia. Now, Indonesia is this group of islands down here. I think they're mostly purple here. Somewhere off, I believe this is right, somewhere off of here there was a major earthquake. The tsunami made its way across this portion of the Indian Ocean. This is called the Bay of Bengal. Across here and hit southern India. Now we have friends who live, whose families live in Chennai. It used to be called, I believe I forgot the name of it. Oh, Madras. There it is in parentheses. Madras, India. Okay? But now its name is Chennai. It's gone to more of the original name. See, a lot of these were English attempts to sound like what they were supposed to be, and they were all pretty badly there. But anyway, they were there. And there were significant people were out on the beach that morning. I think it was a Sunday morning. They were out on the beach just enjoying beautiful, beautiful weather. And that was such a, relatively speaking, short haul there. They didn't get the tsunami warning until just before it hit. And some of them didn't even know what it was. Because the land goes up pretty gradually there, people had to run at least half a mile to get out of the place that's going to be wiped out by that tsunami. And many of them did. There were quite a number of lives lost on the beach there. The friends of ours that are in Birmingham were frantically calling to see if any of their kinsmen, and some of them had been on the beach, but all of them escaped without any damage to themselves. But there was lots of damage all along there. So tsunamis are not things to mess with. And I think I mentioned before, too, two things that physical science has done better than any of political science has ever gotten done is get countries to cooperate. One is the earthquake detections, the seismographs. That's an international agreement, and every country participates in it. And the other is tsunami warning. And all the coastal countries, all the countries that have any coastline at all, participate in that one quite nicely. You know, they share data, they communicate. I wish the rest of the political science would take lessons from the real scientists. No, I didn't say that, did I? Okay. All right. Now let's move to the tides, which I think is also not in this section. Okay? This was in the moon section, I believe, of, that would be chapter 16. I believe that's where this slide would have originally been, or was in our text. Originally it was in this one. And again, and I think maybe we even had this. It seems like we did have it. I'm pretty sure we did. So they've just repeated themselves here. The tides are produced by the Earth-Moon gravitational attractions already described, back in chapter 16. The basic pattern, 2 high tides a day, 2 low tides a day, every 24 hours and 50 minutes. So there will be some days that you only have either 1 high or 1 low tide, but most days you have 2. That 50 minutes there, if you happen to have a high tide right at before midnight one day, it's not going to happen until after midnight the next day. So you only have 1 that day, or low tide, whatever. It can produce a strong reversing tidal currents in narrow bays. Okay? The tidal bore is a wave moving rapidly up a bay as the tide rises, because it's coming in so rapidly. Now this has to be a narrow bay coming in, and the one that's, I think, the most infamous for this, if I'm not mistaken, I don't know if it shows it over here, is maybe around Nova Scotia. That may be it right there, but I can't read the name. I don't think it has a name in it. But it's in Canada. And remember before we talked about this, I think it went up and down 15 stories is the high, low tide. When that high tide's coming in, you better believe there's going to be a tidal bore, wave moving rapidly up the bay as it rises. And I believe there was an Elizabeth George novel. She's a mystery writer, and it was one of those, her main character is Inspector Lindley, and he was not able to catch who did it, though he figured out who it was, but they killed somebody by getting them out into the tidal basin there. And the tide came in, the tide went out, and never produced a body. Okay. So anyway, it's been the thing of fiction as well, but it's based on reality. All right, now let's get to ocean currents. This is beginning on page 64. We've talked about the waves that mix the water mostly near the surface. That's where most of the mixing is going on there. The ocean currents are streams that transport water over large ocean distances along roughly the same path constantly, continuously. Why they're there, what moves them, what motivates them, what gets them going, we don't know. They just are there. Okay? Here's our best guess is now produced by two effects. One is density differences in seawater. Some seawater is denser than other, so denser water tends to go down and the less dense come up, and that might create the start your engines, getting it moving in the first place. The other, going back to what we were talking about, the waves, the winds blowing persistently in the same direction. And when we say persistently, we mean really persistently, and not just get the surface moving, but start dragging along the waters that are underneath as well. Okay? And perhaps winds do blow that consistently and persistently in the same direction, and maybe that does cause some of these. Okay? The denser water, let's do the density currents first. The denser water displaces the less dense water in deeper basins, and that gets the water flowing in one direction, and once it gets going, it just keeps going. Okay? Three influences here for density. Number one, water temperature. Polar water, much colder, the water is much denser than warm water. As anything heats, it tends to expand, and as it cools, it tends to contract. So the contracted polar water, much denser. So the water in the tropics is warmer and less dense, so you have this kind of action going on. The tropical water is moving, I'm talking northern hemisphere, and the polar water is heading underneath. Salinity, we talked about that. Salt accumulation and mechanisms. The freezing of water near the poles increases the salinity near the poles. That makes it denser. The evaporation and runoff in warm pockets, like the Mediterranean, that makes it denser. So you can have, these are related. Well, of course, they're part of the density thing. The more your salt, greater the thing, more to the 36 parts per 1,000 rather than 32 parts per 1,000, that would create some of this density effect. And then the other thing is the suspended sediments. Just think about what the Mississippi has been dumping into the Gulf all year, ever since all the flooding that happened way up north. Where that flooding happened, lots of topsoil got washed away, got eroded. It made it into the rivers. The rivers flooded. They got picked up more. They went on down, and where that went into the Gulf of Mexico, that's pretty dense stuff, okay? That turbidity currents to the oceanic basin hauls it on out there, okay? Here, now, I find this almost hard to believe, but we don't understand beans about the ocean anyway. Here is Greenland, here is Iceland. So we're right up here. Here's Greenland, there's Iceland. So we're right there in the Denmark Strait. Why would they call it Denmark Strait? Denmark used to be the colonizer for Greenland, and may have been for Iceland as well. I don't know for sure there, but I know that it was for Greenland. And evidently someone forgot to tell one of our chief executive officers of the country that they no longer owned it, and he was, I think, going to buy Greenland from Denmark. He said, no, we don't own it anymore. Besides, it's not for sale. Well, we won't get into that. That's the political side. Okay. So, but here we are up here in the Denmark Straits between Greenland and Iceland. Here's cold, dense Arctic water. Remember, this is where, this is more shallow up here. This cold water goes down, and what? Meets Antarctic water at 30 degrees north? Antarctic water at 30 degrees north? That's coming from here. and coming as far here. So you've got a lot of movement going on way, way under there. Okay, that's, I guess they know what they're talking about. 30 degrees north. This is 65 north. Who wins here? I don't know. I would think this would be colder, denser because it's more recently cold. But anyway, you can have quite a bit of motion going on with that. Now, we also have surface currents. Not just the deep, deep currents. We have the surface currents. And some of these global circulation patterns are maintained basically by the patterns of prevailing wind. So the density currents are generally quite deep currents. The prevailing wind currents will be more of your surface currents. They're also influenced by rotation of the Earth, because think about this, the Earth is spinning like this. The water sort of wants to hang where it is, inertia. It doesn't want to move, so you have some of this. So if you have some other currents going on here, like stuff coming up here and then the Earth is spinning here, that could create some circular kind of patterns. Okay? Now, and the ocean basin shapes. And boy, do we understand very little of that too. We don't know what the bottom of the ocean looks like for many parts. North Atlantic, we probably have a better understanding than others because we've gone back and forth. Our Navy has gone back and forth and probably studied these. All the ships they've been trying to find, Titanic was one, and others. They've studied that more than others, but we probably still know just a fraction of what that is really like under there. Okay? Gyres, I guess is how you pronounce that. Great systems of water circulation centered in the mid-latitude. Okay? Just to give you an example, we mentioned before the Gulf Stream comes up and makes a big circular pattern like this. That, I think, is one example of a gyre. They don't do a great job describing it, but great systems of water circulation centered in the mid-latitudes. The direction is dictated, guess what? The good old Coriolis effect. The same thing that produces cyclonic activity in air produces circular patterns in our surface currents. Coriolis effect. You can't get away from it. And that, again, is from the rotation of the Earth. All right. Here are some of the major currents that they've identified here. And the figure in your book, much easier to read than this one. So if you want to look at it, I'll see what I can say here. But here are some of the gyres. Here we have them going this way. Here, this way here. These are in the southern hemisphere. See how these are all going the same way, where these up here tend to be circulating in the opposite direction. Okay, northern hemisphere. Okay, so expect to see that things do opposite on the different hemispheres. They mentioned several. The Falkland currents, I think, are these coming here. Oh, there's just tons of them here. The main one, Gulf Stream, is one that affects us the most, okay? And it may actually be part of that one as well. But here you have a Pacific current that keeps San Diego cool, but keeps Alaska ice-free. It splits here, part goes down, part goes up. Gulf Stream keeps us ice-free. The goodness, I can't remember. Newfoundland, I can't remember what the name of this one is, coming down here, freezes Canada like crazy. Okay, shucks. We got it. So here's one that keeps Japan ice-free, making her a very strong naval power. So you see they're all over the place, contributing things we don't even have a clue about. So here will be some of the places you'll be looking for your lab, either next time or Tuesday. depending on if we go to the weather station or not. All right. Well, what do we know or understand? This is 24.3. Before we get there, on page 626, which is where 24.3 is, ocean floor, there at the top of the page, people behind the science, Rachel Louise Carson. They've mentioned another couple of women in this text. I'm glad they do this. A U.S. biologist, conservationist, and campaigner, basically on conservation, dangers and hazards of many of our modern practices and how that influences environmental. She was a big influencer, inspired the creation of the modern environmental movement. So well worth a read there. If you choose to do a paper on her, this cannot be your source. This can be your idea for it, but you'll have to go and find outside sources, not from the book. Okay, so the ocean floor. Several features of the ocean floor. Now you have to sort of understand what part of the ocean you're in, too. On our eastern shore, we have a large continental shelf. That's an eroded continental margin, relatively shallow water. Okay? This is not a particularly great picture for this, but here is the land, here's the beach. Now picture your Atlantic beaches. They go in and very gradually go up. Same as the Gulf of Mexico. You go in and they just very gradually go up. Out in the Pacific, you come in off the ocean and you've got a mountain range almost immediately. Okay? Very different. No continental shelf in the Pacific. None. Okay? We have this kind of motion there. So let's go back here. So just as the land is going off gradually in the Atlantic, okay, someplace it goes underwater, and that shelf continues. It just is underwater now. That's what we call the continental shelf. At some point, you get to the continental slope, and the continental, I think this is a rise there, going this way, it would be a continental rise. Okay? So what this is basically, now you can look at this either way. This is either built up from erosion coming down this way, and it is filled in here, or this was the beach here at one time, and it's eroded away, and this is what's left of the beach. It's really hard to say which one it is. Probably the latter, that the beach was one time here, but erosion has knocked it down into the water, so you have a continental shelf there. And I know in the Gulf, but it seems like I remember in Virginia Beach and places where I went there, you could sometimes go out and maybe you'd hit some deep areas, but then suddenly you'd be on a sandbar. Someone's sitting way out there on a sandbar. They look like they're walking on water, but you know they're not. It's just that the erosion dug a little ditch here and then deposited the sand further out there. Okay, so there's your continental shelf. And then at some point, though, it does fall off, and that's your continental slope. Steeper transition feature beyond the continental shelf. Often cut by submarine canyons. Now, you can't show this on here, but maybe here you had more erosion here, and you actually have a canyon in here. A ravine, you might say, that's really deep in there. Okay? And this could be things that cause real problems with rip currents, too. Okay, then you get to what they call the ocean basin. And here they say ocean basin floor. They don't really identify it here, but that's basically the same thing you see here. The ocean basin is the deepest, not quite the deepest, but part of the deepest part of the ocean. Okay? Characterized by practically level, and it's abyssal. It's not abysmal, but abyssal plain. But it also has mountain ranges in it. Okay? Now, certainly in the middle of the Atlantic, you have the mid-Atlantic ridge there. That's one thing. But you also have mountain ranges scattered in other places in this otherwise very flat area. Mountains you will never see, okay, because they're so deep into the ocean, okay? Now, talk about the deepest part. These are the trenches. These trenches occur where the ocean basin edges, where they subduct under the continental plates, under the continental plate, or under other oceanic plates. Wherever there's subduction going on, you're going to have a trench. This is usually right near a continent on the other side. Now, most of the time, on the other side where you have a trench here, it goes up pretty quickly because this is a continental crust here, okay? And it usually goes right up. This is subducting under, and you've had it build up. This shows a continental shelf there, but generally, these are not fair, okay? These are much bigger, broader, longer. These hardly exist, but they still may be there, okay? These usually go up pretty abruptly. Just like they're going up here, they continue going up. So I don't like this illustration too much, okay? All right. These trenches are really the deepest part of the ocean, okay? Especially where it's oceanic trench, where one oceanic plate is subducted under the other one, perhaps causing lots of volcanic activity along that. So that's where you get your arc islands, the Aleutians, the Japanese island, the Micronesian, all these islands like that are usually in those chains. Right next to that is usually the very deepest parts. In fact, the deepest part of the ocean that we know of is the Marianas Trench. Okay. Now, you have volcanic peaks like here or here. These are from scattered seamounts, and the Hawaiian Islands are one example of such volcanic peaks. Iceland and the islands around Iceland, another example of volcanic peaks, where they actually have broken the surface. Okay. And here's another one of these illustrations. This one's on page 627 in my book, whatever it is in yours. And these show some of these trenches and ridges and trenches. Okay, of course, this one is the Mid-Atlantic Ridge here. We've talked about that many times. Between Southern Africa and Antarctica, you have another ridge, okay? And then in the middle of the Indian Ocean, you have a ridge. So things must be spreading there. Breaking off of this one between Australia and Antarctica, another ridge, okay? In the Pacific, you have some, generally not as major, because this is where the continents are spreading. This is where they're coming together. So you do have some ridges, and they name several of them here. I won't read all the names to you, but they do have some ridges. But much more prevalent in the Pacific are your trenches. Here's the Aleutian Trench here. This, I can't remember what the name of that one is. The Middle America, I can't read it. Let's see if I can read it in my book. Middle America Trench, Peru-Chile Trench. I thought that's what it was saying, but I thought that's there's a trench here, the Sundra. There's a variety of trenches here. Now, right here, I believe it is. I can't read the book. Yeah, that's it. The Marianas Trench is right here. Now, the Marianas Islands, the most well-known of these is Guam. If you've heard of that, it's a pretty major naval base there. The right, on one side or the other, I don't remember which side, this doesn't really show, is the deepest trench in the ocean. deepest trench in the world. The greatest depth of water is right there in the Marianas Trench. Oceanic plate subduction. Okay, there's the Mindanao here, several others here. Aleutian, I said here, I think that may be a continuation of that. But several trenches that you'll find there. Even one here at Puerto Rico. Okay, unusual for the Atlantic, but it does have a trench there. I think that's at Puerto Rico. I can't read it. Yeah, the Puerto Rico Trench. Right above this whole series of islands here, there's Cuba, Hispaniola, where Dominican Republic and Haiti are, and then Puerto Rico is there too. Okay. That's an island chain, not as major as you see in the Pacific, but a chain of islands that is formed, and that's the oceanic trench there, probably between the North American and South American plates. I don't know that for sure, but my guess is that's what it is. Okay. Now, probably not fair to say, probably not quite scientific to say, but this, the Red Sea here, between Africa and the Arabian Peninsula, that's basically almost like a land trench. Okay, I believe the feeling is this is where the African plate is separating somewhat from the Arabian plate here, and that's why the Red Sea is here. And if you follow this on up, the Dead Sea is right in here, and then you get these others. So who knows what all is going on there? But certainly we know less about what's going on under the water than we do on top of it. Okay. Any questions on the trenches or ridges? What's that? Oh, okay. I think that's the last slide. Oh, shucks. How sad. Now, guess what I'll say next? Nothing replaces reading. Oh, and by the way, it is time, or right at time, to take roll again. So why don't we do that? Louise is still here. Lexi is still here. Zarik has not made it in today. Okay. All right. Brianna, as far as I know, is gone. CJ is still here. Ethan is still here. Amanda's still here. Jordan's still here. Somewhere over there. There you are. I see you. Okay. Jonah and Patrick are still here. Maurice is still here. Cameron hasn't made it in today. Derek, I think we've lost. Tegan hasn't made it in today. Chris is kind of still here. Latricia is still back there. I see her. Evan's still here. Ian is still here. Edward's still here. Maya is still here. And Michael hasn't made it in today. I marked him by mistake. Ken's still here. Maya hasn't made it. Whoa. Oh, I missed Diamond. Diamond's still here. Tamaya didn't make it today. Ruben's still here. And Ryan is still here. Okay. Good deal. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 3, 6, 9, 12, 15, 18, 19. Okay. Now, as I was starting to say, let me get on out of that. Nothing replaces reading the chapter. So please get the chapter read. And when you finish that, you can look at the summary. This is probably about average summary length. Quite a few italicized words here, so quite a few things to pay attention to. Most of those show up in the key terms, which is maybe average or a little below average list. These are given alphabetically, but they do give the page number in parentheses next to that. But then applying the concepts, these are multiple choice questions, 46, which is about normal, maybe one or two fewer than normal. If you have those down, you probably have a pretty good understanding of the chapter. The questions for thought, only 13 questions here. That's a little bit below normal. For further analysis, maybe slightly above normal, 6 of those. Other good things to read and study for the test. And then the parallel exercises, you can do some of those if you'd like, but that's completely up to you. So, we still don't know what Jerry Tracy has, if he's responded or what he'll say. Watch your, let me right now go on and pull up my email again just to see if he's responded while we've been talking. Nope. Nothing new since the last time I looked. Okay. I'll check again before you leave today, just to make sure he hasn't responded. Go on and close this out. And I'll close this out. Okay. So, if he responds and says we can come Thursday, then I'll try to arrange, in the time I've got, to get a vehicle. The van, I don't remember how many the capacity are. It's not huge, but I'll try to get the van if we can get it and take it. So as many as can meet them. If we do go Thursday, we'll meet here at 1:15 and leave here at 1:15. So be here early. If you're not here early, you have to get there by yourself. Now, does everyone at least have a cursory understanding, except Amanda, of where Channel 13 is? Do any of you know where Vulcan Park is? Vulcan, the statue, right? Okay. You go there, you enter as if you're going to the park. It used to be there at the entrance off of, is there at the bottom of Red Mountain on the Homewood side. There's an intersection there. I can't think of the, this is Valley, I believe it is, and this is 21st or 23rd or something like that. And right there where you turn in, there used to be a rotating NBC sign. I don't know if it's still there or not, but anyway, it is still there. So you turn there, go up. Now go up as if you're going to Vulcan, but don't pull into the Vulcan parking lot. Or if you do pull into the Vulcan parking lot, pull into the one that cuts through, and where it cuts through and comes down the other side, there is a road, and it says something like dead end, or no through traffic, or something like that. That's what you get on, okay? No sign saying that's where NBC is or anything else. Alabama 13, anything like that. It's just as a road that says no outlet or something like that. Get on that road and go up there, and you'll see, if you drive for a ways without seeing anything, then you'll see way up there is Channel 13, and on ahead is Fox 6. Don't go as far as Fox 6. You go almost to where you go to Fox 6, and the last turn to the right, you'll see a little bitty sign that says Channel 13. That's where you turn. Not a lot of parking there. There is some, but it's not a lot. So the more you can pool together, the better. Okay? So if so, we're leaving here. The van will be leaving here, if I can get the van, at 1:15. We've got to get there as close to 2 o'clock as possible. This is when he's always asked us to be there in the past. So I just assume it's going to be the same. Now, We used to be able to make it in 45 minutes with no problem. But now the 2059 doesn't go through downtown anymore. They're doing all that construction there. So I don't even know the best way. Do any of you travel that way and have a suggestion the best way to get there from here?
Like Green Springs or something.
Second?
Get off at Green Springs.
Okay.
You could go 5920, get on 65 South. You could get
Okay.
off at Oxmoor or Green Springs and go over to Valley.
Yeah, okay.
It's right there.
Okay. That sounds like a really good plan. So what we'll do is go in from here, go east until we get to 65, go south on 65, and then, like you said, I know you pass 4th and 6th south. You go over, and what's the next exit? Is it?
I think the next exit is Green Springs.
Green Springs. So you get off at Green Springs and then go south on Green Springs until you hit Valley, take a left on Valley, and go. It'll take us a little longer than Expressway almost the whole way. Not quite, but almost. But I think that'll get us there, hopefully within 45 minutes. Okay? So if you miss the van, that's where we're going. 2065, 2059, until you hit 65, go south on 65, go south on 65 until the Green Springs exit, get off there, continue south on Green Springs until you hit the cross for Valley Road. And that's, used to be, was it Jim and Nick? No, Johnny Ray's Barbecue used to be there. I don't know if it still is. But just before you get down into that part of Homewood, Valley Road, take a left and just take that until you see the sign. You'll turn left to go up the mountain again. You've gone across Red Mountain, then you'll go down along Red Mountain and then go up again. And that's where the station is. Okay. Now, if he doesn't get in touch with us or can't take us on Thursday, then on Thursday we will come back in here and have the lab for Chapter 24 and then the test for Chapter 24. And hope he can take us on Tuesday. Okay? If he can't take us on Tuesday, if there's a chance he can take us on Thursday, we'll go on and have the test, the final exam on Tuesday, and then go to the field trip on Thursday. If he can't take us at all, sorry, I forgot all about this. Before the test, we would be giving your reports. So plan to have, if we can't go on Thursday, this coming Thursday, plan, any of you who can, to talk about your paper. And any who do and talk about it, you get 25 bonus lab points. So you can drop a low lab score, or maybe one that you're missing. Okay. And we'll do that for the rest of the time up until Thursday. Unless he takes us on Thursday, then everything we would have done on Thursday will be done on Tuesday, meaning pizza and final exam. And then on Thursday we'll do the field trip. I don't think he'll put it off that long. Hopefully we'll go. Hopefully this coming Thursday, day after tomorrow. All right, any questions? All right. It's awfully early, but are you ready for your test?
Yes.
Chapter 23 test. After this, our filler time is going to be research papers, so be prepared at a moment's notice, okay, to do that. Let me first get rid of this before I lose it.
But we're not doing that today. After the test, then you go.
Yeah, you're leaving today after the test. I've marked the lab time, so we're here. Any other questions before I shut down the recording?